In this lecture, we'll discuss another way of classifying systems, as either causal or non-causal. Before we talk about causal and non-causal systems, let's review the material on signals. What is a causal signal and what is a non-causal signal? A causal signal is any signal that has a value of 0 before time 0. A non-causal signal has a non-zero value before time 0. We say a non-causal signal starts before time 0. Now that we've reviewed the material on signals, let's turn our attention to systems. A causal system is a system whose output at any time t0 depends only on inputs that occur before or at time t0. This must be true for every input and every time t0. In other words, a causal system only depends upon the current or previous values of the input. It doesn't depend upon future values of the input. So here are some examples of causal systems. The first is the differential equation, y dot plus y equals x, where x is the input and y is the output. If, for example, we put a step signal x of t into this system, the output will respond after the input changes. It doesn't anticipate the change in the input before it happens. Another example is the delay system, y of t equals x of t minus 1. The output is a delayed version of the input. So, for example, if we put in the signal x of t shown at the bottom of the page, which starts at time minus 2, the output will look as in the bottom right-hand corner, y of t starting at minus 1. So it's important to point out that the output of a causal system may be a non-causal signal. A causal system means it just doesn't respond until the input does something. If the input does something before time 0, the output can as well, as long as it only responds to the input after the input has happened. In contrast to a causal system, a non-causal system can respond to future inputs. So the output at time t0 can depend upon the input at a time occurring after t0. Here's an example of a non-causal system. Y of t equals x of t minus 2 plus x of t plus 2 divided by 2. What is this system doing? It's saying the output at the current time is the average of the input at 2 seconds ago and 2 seconds in the future. So for example, if we put in the signal x of t, which is a step of height 2 occurring at time 1, then the output will start at time minus 1 because it is anticipating the input x of t increasing at time 1. By the way, this system is a moving average type system. It's just averaging 2 points, one 2 seconds in the future and one 2 seconds in the past. You might be asking the question, why are we even talking about non-causal systems? They seem kind of crazy, the idea that an output could respond to an input before the input has actually happened. So why discuss non-causal systems? Well, first place, it should be pointed out, as you've guessed, that non-causal systems are not physically realizable. We can't know what an input's going to do in the future before it does it. But non-causal systems can still be quite useful. They can be useful for whenever we have pre-recorded data, or when we happen to be working with a signal whose independent variable is not time. And a good example of that is image processing. Another reason why we study non-causal systems is that non-causal systems often provide the very best performance any system can under the circumstances. That can help you understand what the limitations are for an application. Let's suppose you have some sort of performance specification for an engineering system, and you find that even a non-causal system cannot meet that performance specification. Then you're quite certain that a causal system can't, because a non-causal system can act on future inputs and therefore give better performance. For example, let's suppose you're writing an algorithm which will determine what stocks to buy. If this algorithm can only use past values of the stock's price, its performance will be different than if it can use future values of the stock's price. Clearly, if you have access to the future values of the price of a stock, you'll be able to make much better picks in terms of what stocks to buy now. Let's remember again what a causal system is. In a causal system, the output at the current time depends only on the current input and previous inputs. It does not depend upon future inputs. So here's an important fact. Given a causal input signal, a causal system will always produce a causal output signal. That is, if we put in an input signal, like the x of t shown here, that does not start until after time t equals 0, then the output signal will not start until after time t equals 0. This is not true for a non-causal system. For a non-causal system, if we put in a causal input, we may or may not get a causal output. This material about causal and non-causal systems can be quite confusing, especially since we just had a whole discussion of causal signals and non-causal signals. So to see how well you're understanding this, let's have a pop quiz. Our question is, true or false? A causal system always produces a causal output signal. That was really tense now that the country music is gone. So, true or false? A causal system always produces a causal output signal. The answer is false. And here's an example. If we put a non-causal input into a causal system, the output can be non-causal. A causal system just means that the output doesn't respond to future inputs. But if the input is doing something before time 0, the output can do something before time 0 as well. So the output of a causal system can be non-causal. As I mentioned previously, you encountered causal and non-causal systems before, back when we discussed the different types of moving averages. And if you remember, you saw that the causal system would not respond until after the input, while the non-causal system could respond before the input. This meant that the output of the causal system to a periodic signal had to lag behind the input signal. This is a natural consequence of averaging with a causal system. But the non-causal system could respond with the output being in phase with the input. This is one characteristic that non-causal systems may behave, but this is not required of non-causal systems. Checking a mathematical system to see if it's causal is not easy. One has to consider whether any input signal at any particular time might cause the output to respond before the input. A system might act causal for some inputs, but non-causal for other inputs. I have put together a test which you can use to determine causality. Now this test is only a sufficient condition for causality. That means some causal systems may not satisfy this condition, but no non-causal systems should satisfy the condition. So, if this condition is satisfied, you can be confident the system is causal. The first step in using this condition is to write the equation in the proper form. Now I'm assuming here that y is your output. Your first step is to write the equation so that the highest derivative of the output y of t is on the left-hand side, and you're to put all other signals on the right-hand side of the equation. Once you've written the system in the proper form, you're ready to conduct the test. And the test is as follows. The system is causal if all signals on the right-hand side have no time scaling or reversals, have arguments of the form t minus a, where a is greater than or equal to 0, if these terms are not within a time integral, and for any terms within an integral, have values equal to 0 if any signal argument will take on a value greater than t during the integration. The easiest way to show you what's meant by these conditions is to do some examples. Our first example is the system y of t equals x of t over 2. You'll notice the system does time scaling. So if it takes in the signal x of t, which is a pulse, from -1 to 1, it will convert this to a pulse going from -2 to 2. So you can see that the output goes up at time -2, but the input doesn't go up until time -1. So this system is non-causal due to the time scaling. We'll change this system slightly for our second example. Y of t equals x of t over 2 times u of t. What will this do to the same pulse signal? Because of the presence of the u of t step function, any input before time 0 will be ignored. The time scaling for any signal values before time 0 tends to push them further leftward because we expand in the time scaling away from the origin. So signal values before time 0 are pushed leftward, while signal values after time 0 are pushed rightward. Since the step function causes us to ignore all inputs before time 0, the presence of the time scaling in this case does not result in a non-causal system. So this system is causal. The output responds after the input. This example shows you why the presence of time scaling alone can't determine whether a system is causal or non-causal. This is why the condition I gave you is only a sufficient condition. Here is example number 3. Y dot equals y of t minus 3 squared plus the integral from t minus 1 to t of x of tau d tau. If you notice, this one has the form given by the sufficient condition. The argument of the first term on the right-hand side is for time t minus 3, which is in the past compared to time t on the left-hand side. And the integral term is from t minus 1 to t. These are all past or current values of the signal x. So this system is a causal system. Our fourth example is y dot equals cosine 3t y of t plus x of minus t. Now you see a time scaling on the cosine t argument in the first term on the right hand side, but this time scaling is not on a signal. The signals in this case are y and x. This is just a parameter, so this time scaling has no effect on causality. The x of minus t, however, does. This time reversal would not be okay for a causal system. So this system is non-causal. Example number 5 is a bit tricky. It says y of t is equal to the integral from minus infinity to infinity of u of t minus tau x of tau d tau. When seeing that integral of tau from minus infinity to infinity, you would think that x values for times greater than t would come into play in determining y of t. But you'll note that u of t minus tau will be 0 whenever tau is greater than t. And that means that values of x for times greater than t will not actually contribute to making y of t. So this system is causal. Let's have another pop quiz. And our question is, can a non-causal system take a non-causal input and produce a causal output? Let's see how well you're learning this material. So right now, get yourself a fruity drink, sit down and ponder your answer, and in a minute, we'll have the correct solution. So, can a non-causal system take a non-causal input and produce a causal output? The answer is yes. Simple to show this. Consider the system y of t equals x of minus t. That is, the output is a time reversal of the input. This is a non-causal system, and it takes a non-causal input and makes a causal output. If we put in x of t, which was causal, that is, started at time after t equals 0, then this would make an output that started before time 0. So this system is one of those systems which takes a causal input and makes a non-causal output, and takes a non-causal input and makes a causal output. In other words, it doesn't act in a non-causal fashion for every input signal, but it does act in a non-causal fashion for some input signals. As I stated before, and as example number 5 showed, the conditions I gave you for causality of systems are sufficient conditions, not necessary conditions. That is, if these conditions are not satisfied, the system still might be causal. For example, consider the two systems shown at the bottom of the page. The first one of these violates the first condition, labeled A, of our sufficient conditions for causality. The second example violates conditions B and C of our sufficient conditions for causality. Yet both these systems are causal. It would really be helpful to have another tool for analyzing causality of systems. Now, as hard as I've thought about this, I cannot come up with a set of necessary and sufficient conditions for causality. There are just too many cases that have to be considered. But I have come up with some sufficient conditions for non-causality. Let's look at the situation. I'm showing here a Venn diagram for the set of all systems. The set of all systems can be divided up into the causal systems and the non-causal systems. Within the set of causal systems are those that I can prove to be causal via the sufficient conditions I gave you. And within the set of non-causal systems, there is a group of systems that I can prove to be non-causal by some sufficient conditions. This is what I mean by a set of sufficient conditions for non-causality. It's another tool in the toolbox to help you understand how systems can be categorized. So hopefully between the sufficient conditions for causality and the sufficient conditions for non-causality, we can arrive at conclusions about most systems. But there will be some systems which cannot be analyzed on the basis of either of these simple conditions. For those, we have to really think through them on a case-by-case basis. So here are the sufficient conditions for non-causality that I just mentioned. If any of the following conditions are satisfied, the system will be non-causal. The first condition is that after simplifying, the equation contains limits of integration of signals that are fixed values. So some examples of this are shown on the right. For example, if the equation contains the integral from minus infinity to 3 of y of tau d tau, well then the system will be non-causal. The key aspect here is that the limit of integration is a fixed value 3. Also, if we have a term, say, that is the integral from 0 to t of x of tau d tau, that will be a non-causal system, because the lower limit of integration is a fixed value, 0. For this condition, infinity or minus infinity does not count. It's only when we have fixed values like 0 or 3 in our limits of integration. The second sufficient condition for non-causality is that after all integrals have been eliminated by differentiation and the highest order derivative of y of t, the output, is isolated on the left-hand side of the equation, the right-hand side of the equation contains signals with the argument t plus a, where a is greater than 0. So for example, suppose you're given the first equation on the right-hand side here, y of t equals integral from minus infinity to t plus 1 x of tau d tau. You have an integral on the right-hand side, and we need to eliminate it first before we apply this condition. So we take a derivative of both sides, which gives us the second equation, y dot of t equals x of t plus 1. Now x is a signal, and the argument of x on the right-hand side is t plus 1. Here the 1 is greater than 0, and so this equation is non-causal. Another example of a non-causal equation is the third equation in the box on the right-hand side. Y dot of t equals y of t plus 1 plus x of t minus 1. Here you can see it's dependent upon the signal y at time t plus 1. Therefore, this equation satisfies condition number 2 for non-causality, and so this differential equation represents a non-causal system. So within our Venn diagram, we've seen examples of systems which satisfy the sufficient conditions for causality and examples of systems which satisfy the sufficient conditions for non-causality. And as I mentioned before, there will be systems which don't satisfy either sufficient condition. Some of these will be causal, and some of these will be non-causal. We have to carefully think through these cases where neither set of sufficient conditions apply.